Wait, did I just hit record? Did I?
Yeah.
Hopefully.
I think so, yes.
Awesome. Okay. So, attendance. How are we doing on attendance? Let's see. Oh. What do you want?
This would not be your test would it be?
It would. Why do you have it?
I don't know, it's just laying on the little
Because
working station.
those printer things have poltergeists in them.
Yeah, and I figured that's a really good way to somebody to make
Well,
a quick dollar. I
Because
was about to sell it to somebody.
Could you sell it to me next time?
So, because you put your pin in, and it's like, oh, no, you can't print it here because of some kind of paper issue.
Yeah.
So you go to the other one and print it. If you went to the other one and printed it, shouldn't it satisfy?
Yeah, but you have to go in and delete your stuff.
You shouldn't have to delete it if you printed it. Yeah, but I printed it on the other one, so it should, since they're linked in the system. If I went to print it on one and it wouldn't print, and I went to the other and it printed, it should void out of the system. It's junk. It's terrible. That's what you need to know.
Next time they should let you do.
What? Good. You should put them with the other ones.
It's buying paper.
All right. Apologies for the interruption. Even though it's totally not my fault. The computer says everybody's here. Shh. Which means shh. That we should shh. Have 29 people, including the student peer tutor thingamajig. 29. 1 and 2 makes. 3. And 4 makes. 7. And 3 makes. 10. And 6 makes.
16.
And 5 makes.
21.
And 2 makes.
28.
And 4 makes.
27.
Plus, are we missing?
Plus the 2,
Nope.
28, 29.
No.
Plus the 2, that's 27.
The 2 that went out. Okay, there we go. Wait, 2? Oh yeah, because that one didn't want to partake today. All right. Guys, are you ready? You're not ready. You don't even have your computer open. That's fine. You guys don't want your computer open. Go close your computer. Close them. Close them. Close the computer. Close it. You guys want to do no calculator 2 today?
No.
We're doing no calculator today. Guys, you're gonna be like, oh yeah, this is really easy. No, I promise. Guys, yes, I promise. I'm assigning it, but you can't open your computers yet to look at it. 2 reasons for that. 1, close it. 1, close it. One reason I want your computer closed is because I had somebody, a few people earlier today, clearly clacking on the questions before we even went over the lesson. Guys, you got to read the lesson. You've got to do a couple examples. Shh. You've got to watch the video. You got to ask questions, maybe. I don't know. Just throwing that out. Might be crazy. Actually, ask a question if you don't know something, rather than just clickety-clacking and hoping you get it right. Can you clickety-clack and get a 100 because you have a couple of guesses, and maybe you could just ask the Google machine on your homework?
Yeah.
Does that mean you know the content?
No.
Probably means you're going to fail the test. Whatever the test is that's coming for the content that you're not ingesting the proper way. Okay, the proper way is you read, you ask questions. You watch the videos, you ask questions. You do the simulations, you ask questions. You do the examples, you ask questions if you need them. And then you do the actual 1 through 10 for points. And still ask questions if you need them. Very good. Okay, so here we go. The other reason you don't need your computer, well, because I've got it up here. And you don't need a calculator because the math is really simple today, okay? I promise. Notebooks need to be out, though. Notebook. You can have him take it for you because you're a gimp. Okay? Shh. Where's yours? Open it up. Just because your notebook is out, you need to have it open with a pencil. Where's yours? Is it in your lap? Awesome.
Is it 6.2 today?
It is 6.2.
Thank you, sir.
All right, so all the way at the top, 6.2, conservation of momentum in 1 dimension. We're not going to do 2 dimensions because that'd be more higher level. Okay, we're just lowly freshmen. Okay, here is probably one of the ugliest sea creatures of all time, the humpback whale. I mean, guys, it's got barnacles growing on it for crying out loud. It could use like some dry dock time, put it up on a lift or something, scrape off the barnacles, but no, can't be bothered. What? What?
I didn't finish writing.
You don't need to write it down. Okay. Hey, title your notes, conservation of momentum.
Buddy, were you?
That's fine. All right. Can I move on now? Your Highness.
No.
No?
Okay, now you can.
Oh, she'll allow me. I can move on now. Okay, here we go. So there's the ugly fish.
Well, I think it's not ugly.
Somebody. What?
It's
It's a mammal. It's an ugly sea creature mammal thing.
What if you have barnacles down on you?
I would clean them off.
But they literally can't. They don't have
That's
hands.
why they got to go into dry dock. If they would just swim into dry dock, I'm sure the dock workers would be like, oh, it's here for cleaning. Let's help it out.
Well, I understand.
All right. Shh. All right, guys. Calm down. Here we go. For the whale to leap out of the water, something underwater must be moving in the opposite direction with a lot of velocity. Yes?
Yes.
Okay. What part of the whale do you think propels it up out of the water?
Tail.
The tail pushes down upon the water, and the water does what?
Goes up.
Pushes back against the tail, which is which of Newton's laws of motion?
Third.
Third. Oh my goodness. Love it. Love it. Okay, here we go. Conservation of momentum in one direction. When impulse and momentum were introduced, we used the example of a batted ball and the bat. Okay, it's really obvious. I'm just gonna paraphrase here. It's really obvious that the ball is flinging off the bat, is changing direction of travel 180 degrees or more, and it's going off in a pretty quick clip. Yes, unless it was like a bunt, right? Bunt.
Yes.
But the change of momentum on the bat is going to be the exact same as the change of momentum on the ball. Does that make sense?
Yes.
It might not, because it's not obvious. Because while the ball changes direction entirely and probably speeds up, again, unless it's a bunt, the bat is going to be swung, hit the ball, and follow through. It's going to keep moving in that same arc, that same swing. So, allow me to try to demonstrate, not miss and make a fool of myself. Like that. I'll try again. I will try again until I really make a fool of myself. Okay, it hit right here. The bat kept going through until I stopped it, right? So it's not super obvious, but I felt it. This tiny, does that weigh much? Does that have much mass? No. But I felt the impact. And my hands absorbed that, but the momentum of the bat and my arms moving forward has more what than the ball?
Momentum.
More momentum.
Has more acceleration.
More momentum because it has more M word. Mass. It's got more mass.
I said mass.
So the change in momentum between the two is actually the same. Okay? But because this has a lot less mass, it's going to have a bigger change in velocity. Good. All right, cool. So there's that. That was the whole paragraph. Change in momentum of the ball, obvious, cool. That was another paragraph. All right, consider another system. Internal force, ice skaters. Oh no, I'm done with ice skaters. Here we go. Closed systems. For your notes, under where you have written conservation of momentum in one direction. Or not direction, one dimension, excuse me. Write down in a closed system. That's what we're talking about today, in a closed system. Momentum is always conserved. You don't lose momentum. And for today's lesson, you won't even lose it, air quotes, to friction, because we're not going to consider friction today. The only way you can, air quote, lose momentum is if it's converted, so you're not really losing it, it's being converted to friction. But we're not going to consider friction today. Does that make sense?
Yes.
I hope so. So here we go. You've got the word definition right here. In a closed system, momentum is always conserved. And then we have this formula that I wrote on the board as well. We have P, which means what?
Momentum.
Momentum. Momentum, ball A, or object A, B for before. So momentum of object A before a collision, plus momentum of object B before a collision, so those two are colliding, their individual momentums combined, added together, will equal their combined momentums after a collision between the two. By the way, it didn't matter if I have 2 objects colliding, 3 objects colliding, or 150 objects colliding. Their combined momentums will be the same as their combined momentums after. Their combined momentum before equals the combined momentum after. That is the law of conservation of momentum. Are we clear?
Yes, sir.
If there was any loss, air quote, of momentum, it would be because as they collide, there's some squishing, perhaps, some things flown off in other directions. By the way, that'd just be a new object from the old object, so it would still follow that law. But if they're squishing, what would be created? So if you have like tennis balls, you're going to see this example. There's tennis balls hitting each other. When they bounce off, what does the skin of the tennis ball do? They flex, right? That flex of the tennis ball is going to result in an F word, friction between the two objects and within each individual object as they flex. So that momentum energy will be converted to what? Heat, right? Cool. But we're not going to deal with friction in today's lesson. So here's our formula. Let's watch this video and then we'll work an example, okay?
The total momentum remains the same. So for example, if I can get these two to stick together, while one is stationary and the other is moving towards it, once they stick together, the total momentum will remain the same, so the combined objects will have half the velocity of the one initially that was moving. Conservation of momentum makes it actually quite interesting and challenging to move around the ISS if you don't have something to reach onto a handhold. Because if you get trapped out in the middle, there's no wiggling you can do, no swimming you can do that will get you over to a handhold so that you can pull yourself to move through the station. Because no matter what I do here, if I just stay floating in the middle, I'm just going to remain here in the middle since the total conservation, since the total momentum of the system has to remain constant.
Okay, does that make sense? Hopefully that helps. Yes, no, maybe?
A little bit.
If you have more questions later, please bring them up. Okay. We're going to work a problem. Now, when you guys work example 2 on your own, and this one right now, don't go down below the problem, because it's going to show you how to work it out, but we're going to try to work it out on our own first. Does that make sense? Let's try to work it on our own. So we've got 2 balls, ball A, ball B. I had some Snickers earlier, from you all, not like the candy, but some people were snickering because we're talking about 2 balls. Anyway, ball A, I want you guys to take a minute and draw out the scenario. I want you to visualize and then represent it on your paper. Ball A is traveling west. It has a mass of 2 kilograms and a velocity of 2 meters per second. Write it down. I don't care if you have to put it in a table of known things or if you can take it straight from there and put it on a piece of paper. You can't see that far? I'm telling you, write it down. I'm telling you the things in the stuff. Write it down. Ball A, mass 2 kilograms, velocity 2 meters per second, west. It's moving west. Ball B, 4 kilograms, velocity 1 meter per second, also west. And then it goes on to say that object A, ball A, is going to catch up to and collide with ball B. So if they're both going west, on a map, which direction is west? On a map. Left, right? Usually. I mean, could you make a map where it's flipped around? Yes, but why would you? It's not the standard. So we probably have, they're both going the same direction, right? So have an arrow for both, same direction. A is catching up to B because A is going faster than B, yes? Okay, so start visualizing that, putting that down on your paper. I'll catch up to you. Is that showing up all right for you, that orange?
Yeah.
Both of them are going west. A, B. They're both going west, but A is going faster, and it says it's going to catch up to it and collide with it. This one was 2 kilograms, 2 meters per second. This one's 4 kilograms, 1 meter per second. Ball A overtakes ball B and collides with it from behind, rear ends it. After the collision, ball A is moving westward, so it's still going that way, but it's reduced in velocity down to 1 meter per second. Okay, cool. And the question says, what is the velocity of ball B? We've got our formula. What can I start putting into my formula? Do we have any of these variables? By the way, how many variables are here? How many things, how many pieces in this formula?
Oh, 2.
4. 1, 2, 3, 4. We have momentum for A before and after, momentum for B before and after. Do we have any of those 4? Or do we at least have the pieces to get? These are all momentums. What is momentum? Think math. What is momentum? What? Momentum is mass times velocity. So we're going to say P is equal to mv, mass times velocity. Thank you. So do we have any of those?
Yeah.
Which ones do we have?
Both.
Both? How about 3? We have 3 of the 4, guys. Somebody give me 1.
4 kg.
What?
4 kg or 4 kilograms.
Great, that's one of our components. What of these do we have? So, for example, can somebody give me the momentum of A before the collision?
Yes.
What is it?
2, whatever.
You guys are guessing.
Wait,
What is momentum? Mass times velocity. So look at our scenario for A, ball A. Do we have mass and velocity?
Yes. 4.
Okay, so for what?
Meters per second.
4 kilogram meters per second. You can't just decide which of the units you take. You take both because we're multiplying. So right here, you're going to have 4 kilogram meters per second. Plus, do we have the momentum for ball B before the collision?
Yes, 4 kilograms.
4, because 4 times 1 is 4. So we got 4 kgm per s. Again. And it's going to be equal to the after momentum. So do we know either of those?
No.
We don't?
Yes, we do.
My screen's going nuts by itself. Here we go. Let's scroll back up to where we were. There we go. It tells us that after the collision, ball A is moving at 1 meter per second. Momentum is mass times velocity. It tells us that after its velocity is 1 meter per second. Did its mass change?
No.
So what's its momentum after the collision? A. 2. Because it's still 2 kilograms, but it's only moving at 1 meter per second. So 2 times 1 is good. Boy, I swear my mouse is just scrolling on its own. That's fine. We don't need it. 2. No, it'd be 2 kilogram meters per second. Plus, now, can we know the momentum yet? Are we given the momentum of ball B? No. So we're going to leave that PBA, momentum of object B after the collision. Now, guys, I know you said you didn't want to do any hard math today, and I told you no calculators. I think you guys can do 4 plus 4, can't you?
Oh, very hard.
What is it? 8? I heard one bit. Everybody else is joking, I hope. Yes, 8. 8 equals 2 plus PB. Our variable. Hold on, don't jump ahead. Some people might not know what plus 2 is going to equal 8. So what is the opposite of addition?
Subtraction.
So to isolate the variable, we need to subtract 2 to get it out of there.
Oh, this is hard.
And then we need to do it from the other side too. 8 minus 2 is?
6.
See, you were completely right, but 6 equals the PBA. 6 what? We plug it in here. 6 what? Kilogram meters per second, because it's a momentum. Now, are we done?
No.
We're not?
Yeah, we are.
We are?
No.
Yes.
We were looking for momentum.
Yeah.
What was the question? You forget, don't you? We weren't looking for momentum. We were looking for what is the velocity of ball B after the collision. We don't have the velocity, we have the momentum. But do we have the mass?
Yes.
So can't we find the velocity?
Yes.
What is momentum?
Mass times velocity.
So if we want velocity, we can divide out the to isolate the velocity. So really, momentum divided by equals velocity. So let's plug in what we have. What was the momentum?
6 kg.
6 kilogram meters per second. It's important to put the units. You'll see here in a second. What is the mass
2
of ball B?
4
There we go, 4 kilograms. Divide 6 by 4. 6 divided by 4. How many times can 4 go into 6?
0.
1 and a half. Because 4 into 6 leaves 2. 2 is half of 4. Right? Or you can do it this way. Hey, 6 divided by 4. How many times?
1.
How many times? 4 goes into 20. 1.5. Okay? So 1.5 what?
kg meters.
Shh, no!
Kgs
We're
per
dividing.
meters per
Look,
second.
kilograms by kilograms gives you what?
Meters per second.
All that's left. Yep. And that makes sense, doesn't it? Since we're looking for the velocity of ball B. You understand?
Yes.
A little bit.
If you look, a little bit's fine. We'll try to increase that. You guys need to do example 2 by yourself, and then if you still have time, you can work any other examples. And there's a simulation right here that you can do. Look at the summary, review. Oh, there's review questions if you still have time. Otherwise, we'll work those tomorrow, and then we'll do 1 through 10 for a grade. Does that make sense?
Yes, sir.
Well, they give you a lot of practice there. That's good. All right, you're turned loose, but don't do the questions 1 through 10 for a grade. Okay?
Yes,
All
sir.
right.